Please enter the following information. It will be used to create a certificate you can print to show proof of completion for facility access if your department requires it. In this course, we will discuss identification, hazard awareness, and controls when working with lasers. Before we begin, please note that you can read the information presented without having to listen to the narrator at any time by clicking on the script tab. To disable the audio, click on the sound icon at the bottom. Also, this is an interactive tutorial. You will often be prompted to click in an area or make a decision before proceeding to the next section of the course. Finally, if you have sufficient experience in the subject matter, you can test out by clicking on the test button. Please note, however, that if you fail the test, you will have to take the course again until you pass. To begin a lesson, please select a topic. By the end of this module, you should be able to determine laser classes and components. What is a laser? LASER is an acronym which stands for Light Amplification by Stimulated Emission of Radiation. You may find lasers on campus in biological, chemical, and engineering research. The international hazard symbol identifies the presence of different classes of lasers. Laser light is different from ordinary light, like the type you find in a light bulb. Ordinary light is incoherent. This means that it has many wavelengths that move in many directions and thus can emit many different colors. This results in a light that has low concentration of power per surface area. In contrast, laser light is coherent. This means that the light rays have the same wavelength that move in unison, travel in one direction, and have one specific color of light, or what is known as monochromatic. This results in a narrow laser beam that has a high concentration of power per surface area. All lasers have three common elements: a pump, lasing medium, and an arrangement of two mirrors. The pump produces energy used to excite the lasing medium. Examples of sources include flash lamps, electricity, chemical reactions, and other lasers. The lasing medium is a substance that emits coherent light as a result of exposure to the pumping system. Two mirrors form a feedback mechanism. When light is bounced back and forth between the mirrors, its energy is amplified, hence the term stimulated emission. The amplified light escapes from the partially transmitting mirror, also known as the optical resonator, resulting in an actual laser beam. The pump controls the laser's output power, while the lasing medium determines the wavelength. Meanwhile, the mirror controls laser beam stability. Lasers differ from each other based on its output characteristics. It can be a continuous wave or a pulsed laser beam. Continuous wave lasers emit beams at a constant power, similar to a flashlight, for at least a quarter of a second. This is enough time for serious eye damage if the laser has a high enough power. Power for these lasers is expressed in the form of watts. Pulsed lasers emit beams in a single pulse or a train of pulses for a period less than a quarter of a second. If you're struck in the eye by one pulse, you are unlikely to be struck by a second pulse due to this time gap. However, pulsed lasers are usually more hazardous than continuous lasers because the peak power for each pulse can be very high, causing biological damage to the eyes and skin. Energy for these lasers is expressed in the form of joules per second. Knowing how a laser works enables you to better control its beam. Let's review these elements. Which component can be adjusted to control the output power or energy of the laser? Click on the diagram to select your answer. The pump controls output energy. Which component can be adjusted to control the beam stability? The mirrors, also known as optical resonators, can be adjusted to control beam stability. Which component determines the wavelength of the laser? That is correct. The laser medium determines the wavelength of the laser. The basic components of lasers include the pump or energy source, lasing medium, and mirrors or optical resonator. Lasers differ from each other based on the kind of lasing medium they use. It can be a gas, such as argon, solid state, such as a ruby crystal, liquid or dye, or a semiconducting material, such as a diode. Let's review. The laser used to remove the tattoo in this scene is an example of a Q-switched neodymium YAG laser. It is one of the most widely used laser sources for moderate to high power, using a neodymium doped crystal yttrium aluminum garnet to generate a pulsed laser. What type of lasing medium is this? You are correct. The neodymium YAG laser is an example of a solid-state laser system because it uses a crystal to generate a pulsed laser. These types of lasers are rugged, simple to maintain, and capable of generating high-powered pulses, so make sure you use appropriate laser safety eye protection. Lasers are classified according to risk. The American National Standards Institute, or ANSI, categorizes these risks ranging from Class 1, the lowest, to Class 4, the highest. These classifications have different requirements for engineering controls, administrative controls, and personal protective equipment. Select a laser class to learn more. When you're ready, click on Next to move on to the next section of this training. Laser classification schemes were developed to help you gauge the level of risk. As you approach lasers, read the affixed label. Keep in mind that Class 3B and Class 4 lasers are the most hazardous. In fact, these are the only lasers regulated by the University of California. Let's view. Lasers differ from each other based on which type of component they use. That is correct. Which laser class is the most hazardous? That is correct. In summary, remember to determine laser classes and components before beginning work. This includes determining how basic components of a laser works, recognizing different types of lasing mediums, and gauging risk using classification systems. By the end of this module, you should be able to identify biological effects and non-beam hazards of lasers. When used improperly, lasers can cause injuries. The organs affected by exposure are the eyes and skin. Some lasers can cause delayed effects after low-level exposures over long time periods, perhaps even for years. Most effects, however, are immediate, following acute, brief exposures lasting seconds or even much less. Examples of two very dangerous lasers include the xenon monochloride gas excimer, which causes cataracts in the eyes, and the neodymium YAG laser, which causes most skin injuries. Become familiar with the most common types of exposure so that you can help prevent injury. Today's laser light covers three ranges of the electromagnetic spectrum based on their wavelengths. Ultraviolet or UV light has a wavelength between 200 to 400 nanometers. Visible light has a wavelength between 400 to 700 nanometers, and infrared light has a wavelength between 700 to 1 million nanometers. Your eyes are the organ most at risk from laser use. Different wavelengths cause varying levels of hazards to the eyes. The pathological effects of UV lasers include photokeratitis, equivalent of sunburn to the cornea, and photochemical cataracts, clouding of the eye lens. Ultra-short pulse lasers can also cause serious retinal damage. Visible light damage includes photochemical and thermal retinal injury, including blind spots and blurred vision. And infrared lasers cause cataracts, retinal burns, corneal burns, aqueous flares, and or infrared cataract. Blue light, such as argon lasers, and violet light can present what is referred to as a blue light hazard. An example of this is a retinal injury produced by staring at the sun during solar eclipses, staring at the arc produced during welding without eye protection, or staring at blue LED lamps. Thus, Make sure you protect yourself from this visible light by preventing lengthy exposure greater than 10 seconds. This hazard can create a photochemical retinal injury that may go unnoticeable until 24 to 48 hours later. Keep within the maximum permissible exposure limit for the type of laser you are using. This is a level to which an unprotected person may be exposed to laser radiation without adverse biological changes in the eye or skin. Laser levels above this limit requires protective eyewear specific to the wavelength of the laser. How a laser light gets reflected contributes to its hazard. You can get a laser eye injury in one of three ways: intrabeam viewing, specular reflections, and diffuse reflections. Intrabeam viewing is where the eye is exposed to all or part of a laser beam. Specular reflections is when the beam hits a flat surface, such as a mirror, and is reflected in one direction. And diffuse reflection is when the beam hits a rough surface and is reflected in many directions. Lasers that have shorter wavelengths, such as those in the UV region up to 350 nanometers, easily disperse off of rough surfaces through diffusion. In contrast, lasers that have longer wavelengths, such as those above 350 nanometers, tend to disperse easily off of flat surfaces through specular reflection. Your body has a natural aversion response when it comes in contact with a laser beam. Your head will tend to turn and your eyes naturally blink. This response occurs every quarter of a second and is used to calculate laser hazards. However, because it may not always occur in all incidents, you should not rely on this response as a substitute for laser eye protection. In fact, your blink response only works for visible light and not UV or infrared wavelengths. Use your senses to check for eye injury. There are different effects on sight, feeling, and hearing. Exposure to a visible laser beam can be detected by a bright color flash of the emitted wavelength and an after image of its complementary color. For example, a green laser would produce a green flash followed by a red after image. When the retina is affected, there may be difficulty in detecting blue or green colors secondary to cone damage, and pigmentation of the retina may be detected. Exposure to an invisible carbon dioxide laser beam can be detected by a burning pain at the site of exposure on the cornea or sclera. Retinal damage may be associated with an audible pop at the time of exposure. Visual disorientation due to retinal damage may not be apparent to the operator until considerable thermal damage has occurred. Exposure to a Q-switched neodymium YAG laser beam is especially hazardous and may initially go undetected because the beam is invisible and the retina lacks pain sensory nerves. In addition, different wavelengths can also damage the skin. The pathological effects of UV lasers include accelerated aging or increased pigmentation, erythema and cancer, burns, and pigment darkening. Visible lasers can also cause region burns and photosensitive reactions or sun allergies. Some compounds can increase skin sensitivity to ultraviolet radiation injury. This includes antibiotics, antihistamines, and cardiovascular drugs. Always read the labels on medication bottles to alert you to this risk. Thermal damage dominates with pulsed lasers at any wavelength. In the event that a person suffers a laser injury, quick actions need to be taken. First, make sure that the laser involved is turned off, unplugged, and is not in use again until it can be determined that it is safe. Immediately seek medical treatment. Do not permit anyone to delay getting attention. Minor skin damage can often be treated with first aid. Typically, however, people who suffer from serious injuries involving bleeding, severe burn, or intense pain, or from any eye injuries need to be transported to a medical facility as soon as possible. Do not allow injured people to transport themselves since they could be in shock or have impaired vision. Those with eye injuries should be kept calm and in an upright, seated position to minimize blood pressure to the eyes. Finally, notify EH&S or the laser safety officer if you suspect a laser eye exposure. Let's review. Drag and drop each definition on the right to match with the correct concept on the left. That is correct. All too often, laser users become so focused on protecting their eyes and skin that they forget about the hazards around them. These include cuts, exposure to electricity, cryogens, chemicals, fire, inadequate housekeeping, excessive noise, and high pressure. Of these non-beam hazards, which do you think are the leading causes of injury when working with lasers? Next to eye injury, the most common laser injury is electrical shock. So far, all deaths related to lasers have been from electrocution. These deaths occurred while people worked on high voltage power supplies. In addition to discussing electrocution, we will focus on non-beam hazards related to chemicals or toxic substances and fire. These are hazards you are likely to encounter during your work with lasers. Many lasers have high voltage power supplies that can present a risk of electrocution unless sufficient care is taken when servicing them. Thus, ensure that you eliminate any contact with high voltage equipment. Do not perform electrical service or maintenance on a laser unless you are properly trained. Allow the experts, including the service representatives for the laser manufacturer or the campus electricians, to make any necessary repairs. When there are known issues with equipment, lock out or tag out the equipment until it is safe to use. Make sure that you inspect cords, plugs, and accessories for missing or damaged wiring. Look for shorts and overheated components. Do not overload circuits or outlets, place near water, or wear metal objects around electrical equipment. Ground all equipment and complete training in basic electrical safety. If personnel in your work area are working with high voltage power supplies, then Environmental Health and Safety recommends that you take a first aid and CPR class. If you should witness someone being electrocuted, take the following actions. First, kill the circuit if you are able to do so safely. This involves pulling the plug on a laser system or other energized device. Arrange for someone to call 911. Then, remove the victim from the circuitry using a non-conducting material, such as a wooden broom handle. Then, initiate CPR, but only if you are trained. Untrained persons can do more harm than good. Liquid phase dye lasers employ various dyes, some of which are carcinogenic or mutagenic. Therefore, you must mix these dyes in a fume hood while wearing appropriate personal protective equipment, which includes a laboratory coat, eye protection, and impermeable gloves. Dyes should be kept in secondary containment. Also, make sure you review the safety data sheet for each toxic chemical prior to mixing the solutions. Excimer lasers involve the use of fluorine or chlorine gas, both of which are very toxic. These gases need to be stored in approved ventilated gas cabinets. In rare cases, halogen detection and alarm systems or halogen gas scrubbers must be used. When a high-power laser beam strikes certain surfaces or targets, it can vaporize the material and generate toxic gases and particulates into the air that can be harmful if inhaled. When using a high-power beam, make sure that the laser area has either the ventilation rate necessary to reduce pollutants to safe levels or local exhaust systems to remove pollutants altogether. Class 4 visible and infrared beams can ignite certain substances. Lasers with irradiance greater than 10 watts per centimeter squared have the potential to catch on fire. In addition, fire hazards are present when there are improperly ventilated beam enclosures and flammable dyes in use. To avoid fires, keep flammable chemicals and ignitable materials well away from high-powered laser beams. Beam enclosures, barriers, and other components need to be made of fire-resistant materials. Ensure that there are fire extinguishers nearby and that people in the area know how to operate them. Protect against collateral radiation by shielding against X-rays, plasma radiation, RF, and microwaves. Let's review. Who should not perform repair of a high-voltage laser? That is correct. To prevent fire hazards, separate flammables, construct with fire-resistant materials, and keep wet nearby. That is correct. In summary, remember to identify biological effects and non-beam hazards of lasers. This includes wearing eye protection, recognizing the signs and symptoms of injury, following emergency procedures, reducing risk of electrical hazards, avoiding chemical, liquid, or gas exposure, and preventing fire. By the end of this module, you should be able to implement ways of protecting yourself. Engineering controls are physical structures that eliminate or reduce your exposure to dangers, such as electrical and optical hazards. They are the first line of defense. Some engineering controls are required to be installed by the laser manufacturer. This includes protective housing, aperture beam blocks, shutters or attenuators, interlocks and automatic cutoff switches, and warning lights. Another engineering control is known as a beam attenuator. These are mechanical devices designed to decrease the power per unit area of laser beams through absorption and scattering of the beam. Because it blocks bodily access to high laser radiation levels without the need to turn off the laser, these devices are required for Class 3B and Class 4 lasers. Other engineering controls are installed in the facility by laser users. Access control is accomplished by installing locks or security systems, such as keypads or security door cards. Post warning signs in conspicuous areas to prevent unauthorized access. Test warning lights to ensure that they provide an electronic signal when lasers are in use. Contain lasers to a specific area using barriers, such as a laser safety curtain. Place these curtains at entryways to limit exposures greater than the maximum permissible exposure limit. Create a storage space for personal protective equipment, such as safety eyewear, near the entryway. Ensure warning labels are affixed onto the equipment itself, beginning with Class 2 and Class 2M lasers. Interlock interfaces are the primary means of arming and disarming laser interlocks and should be placed near the laser table. Finally, ensure that fire extinguishers are placed within reach in case of an emergency. Please note that this room layout is only a sample. The campus laser safety officer will provide a proper and thorough evaluation to maximize engineering controls. For details regarding the engineering controls required for each laser class, refer to the Laser Safety Manual. Let's review. What kind of warning equipment can you use to provide an electronic signal to indicate when lasers are in use? That is correct. Engineering controls are what that can isolate your exposure to hazards. That is correct. You can contain lasers to a specific area using barriers, such as a what? That is correct. Administrative controls are your second line of defense against laser hazards. These controls focus mostly on policies and requirements that enable people to conduct their jobs safely. There are requirements that are imposed upon people, such as ensuring that all individuals complete laser safety training prior to working with or around lasers. In addition to this online training course, ensure that hands-on training is completed. Minimize risk by restricting access to areas where lasers are used. Develop and follow standard operating procedures and the Laser Safety Manual. Additionally, ensure that you obtain the proper permission to work with lasers by registering your laser machine with Environmental Health and Safety. Finally, ensure that you post the proper warning signs and labels to identify the hazards that are present. Make sure to post the appropriate warning signs on the walls or doors where lasers are present. There are 3 signs that have different messages. Notice signs indicate that alignment, installation, repair, or servicing of lasers is in progress. Caution signs indicate the presence of low-powered Class 2, 2M, and 3R lasers that do not exceed the maximum permissible exposure limits. Warning signs indicate the presence of high-powered continuous wave lasers, Class 3B and most Class 4, or for unattended operations of high-power lasers. And danger signs indicate that extremely high-power multi-kilowatt Class 4 or pulse lasers with exposed beams may be in use, which may result in serious injury or death. Let's review. Which sign indicates the presence of low-powered Class 2 or 2M lasers? Yellow caution signs indicate the presence of low-powered Class 2 or 2M lasers. Which sign indicates that the area is under temporary control for service or repair? Blue notice signs indicate that the area is under temporary control for service or repair. Which sign indicates the presence of Class 4 extremely high-powered or pulse lasers? Red danger signs indicates the presence of Class 4 extremely high-powered or pulse lasers. Which sign indicates the presence of high-powered Class 3B lasers? That is correct. Orange warning signs indicate the presence of high-powered Class 3B lasers and most Class 4 continuous wave lasers. Let's review. Which of the following is an example of an administrative control? That is correct. When you cannot use equipment or policies, implement work practices to reduce the likelihood of injury. These are actions you can take to prevent injury. Generally, work practices are things you want to do to stay safe, regardless of whether you have to do them because of a policy. What do you think? When do most injuries occur when working with lasers? That is correct. Over 60% of incidents occur during alignment procedures. Most go unreported during the critical first 24 to 48 hours post-exposure. Therefore, take care to follow safe work practices during alignment of lasers. An alignment is a tune-up procedure often required for beam out-of-the-box devices. To safely perform an alignment, make sure you remove metal jewelry, watches, and badges before beginning any activities. Prepare all equipment and materials prior to beginning. Use non-reflective tools. Arrange for someone else to be present. Remove unnecessary equipment, tools, and combustible material to minimize the possibility of stray reflections and non-beam accidents. Make sure to keep objects out of the beam. Other examples of work practices include wear personal protective equipment at all times during operation and when a low-powered laser enclosure is open. Reduce the beam power using filters, beam splitters, or dumps, or the lowest possible power supply. Avoid using high power during alignment. Label the areas where the beam leaves the horizontal plane. Work around or avoid beam paths that are at sitting or standing eye level. Direct beam away from eye level and keep body parts out of the beam path. Simulate the beam path using lower power visible lasers. Terminate any stray or unused beams. Use beam shutters to block high power beams anytime they aren't needed. Terminate the beam at the end of its useful path. Eliminate all beams and reflections prior to high power operation. View invisible beams with IR or UV cards or sensor cards, taking care to avoid specular reflections off some of these materials. Do not look directly at the beam. You can prevent from intentional intrabeam viewing with the eye by using cameras or fluorescent devices to view the beam. What do you think? What should you do before removing the protective housing for embedded lasers? That is correct. When performing alignment, make sure to remove jewelry, use non-reflective tools, and what? That is correct. Prevent intrabeam viewing by using what? That is correct. Using personal protective equipment is another way of protecting yourself through the use of a physical barrier. Because there should be other controls implemented, it should be considered the strategy of last resort. This is mainly because there are problems that may arise from its use, such as incorrect fit, use of the wrong type for the job, use of damaged or poorly maintained equipment, or inconsistent use overall. Laser safety goggles or face shields must be worn when working with Class 3B or 4 lasers. Safety eyewear protects you from a diffuse reflection, but not from a direct hit, intrabeam or specular. Gloves protect hands in areas where hot work such as welding or cutting or chemicals are present. Body protection, such as a laboratory coat or a long shirt with sleeves, minimizes chronic exposure to scattered light, such as UV rays that diffuse during excimer laser applications. Laser light can be attenuated by layered clothing. However, do not wear nylon-based material because it transmits 20 to 40% of light through to you. Use aprons and jackets for protection against UV exposure and fire-resistant materials when working with high-powered lasers. Finally, closed-toe shoes should be worn around heavy equipment that can be moved. What do you think? Which safety eyewear can protect against lasers? That is correct. Safety eyewear that protects against optical radiation can shield the eye from laser beams. Special lenses allow light to be absorbed, transmitted at a lower level, or simply blocked at one end of the electromagnetic spectrum. But not all laser eye protection is the same. The kind of lens you use should be based on the wavelength of the laser you're working with. The wavelengths of lasers place them on different parts of the electromagnetic spectrum. For example, argon lasers tend to have shorter wavelengths of 488 nanometers, while neodymium YAG lasers will have a longer wavelength of at least 1060 nanometers. Approved laser safety eyewear is labeled with information about the wavelength that it can help protect you against. This information is generally labeled on the lens itself. What do you think? Dr. Mackenzie needs to protect her eyes during the use of a solid-state ruby laser at a wavelength of 694 nanometers. Which laser eyewear can give her the minimum protection she needs? That is correct. This laser safety eyewear provides protection against lasers with wavelengths between 689 to 782 nanometers. Since the solid-state ruby laser being used has a wavelength of 694 nanometers, Dr. Mackenzie's eyes will be properly protected. The ability of a lens to filter out a laser's wavelength is called its optical density. The relationship between optical density and the amount of laser beam that is transmitted is shown in this table. For example, a safety eyewear that has no optical density, such as in regular prescription glasses, will allow 100% of light to pass through its lens. If the lens, however, was treated and it was rated with an optical density of 1, then it only allows 10% of the laser beam to pass through. In many cases, an optical density that is too high may restrict your ability to see your work, and you'll have trouble pointing or aiming your laser. An optical density that's too low allows too much of the laser beam to pass through and can damage your eyes. So how much is laser light transmission safe to be exposed to? Is it 10% or 1/1,000,000th of a percent? In other words, how do you know which optical density rating to choose? The minimum optical density rating you should choose depends on how much power or energy your laser produces. For example, this sign indicates the presence of a Class 3B laser with a maximum output power of 80 milliwatts. This output power exceeds an optical density of 1, but can be used with safety eyewear that has an optical density of at least 2. You should always consult with your campus laser safety officer to obtain the correct minimum optical density required for the lasers you're working with prior to obtaining laser eye protection. Similar to the wavelength, laser safety eyewear is labeled with the optical density appropriate for its use, as shown in this example. This particular eye protection can be used with infrared light. If used with lasers with wavelengths between 800 to 839 nanometers, this protection will allow you to see 0.1% of the laser beam, since it has optical density of 3. It's important to remember that eyewear only protects you from a diffuse reflection and not from a direct hit, intrabeam or specular. Some eyewear is designed to protect against several types of lasers. What do you think about this situation? Dr. Ducut has determined that she needs a high optical density of 6 to use with a laser that has a wavelength of 930 nanometers. Which safety eyewear can provide her the protection she needs? That is correct. The safety eyewear is labeled with the correct optical density of 6 and can sufficiently protect against a wavelength of 930 nanometers. Select laser safety eyewear based on the optical density and wavelength of your laser. In general, orange eyewear is commonly used for protection against blue and green laser beams, such as the gas ion argon and krypton lasers. Green eyewear is typically used for protection against high-powered lasers, such as a solid-state neodymium YAG, gas ion argon, and Excimer laser. Consult the laser safety officer for more information. In addition to the optical density and wavelength, make sure to select safety eyewear based on proper fit, field of vision, whether prescriptive lenses are required, whether they will allow you to see the glow on sensor cards if used, and the possibility of degradation, such as photo bleaching. In summary, remember to implement ways of protecting yourself. This includes isolating laser operations using engineering controls, following policies and requirements and administrative controls, and wearing personal protective equipment, especially safety eyewear, appropriate to the optical density and wavelength of your laser. To receive credit for this course, you must complete the test. When you're ready, proceed to take tests. Which laser class is the most